Kia ora koutou, no mai, haere mai. Welcome to lesson 18 for introductory physics. In this lesson, we're going to keep looking at collisions. We've defined collisions, we've looked at what happens with momentum and with energy, and we've stuck mostly to one-dimensional problems, although I did briefly mention that momentum is a vector and you can decompose two-dimensional vectors into your different axes. So that's what we're going to continue with today. We're going to look at two-dimensional collisions briefly. We'll just look at a couple of examples of that, but then we're going to look at a couple of other scenarios as well that you might not initially think of when you're thinking of the term collision. As usual, we'll jump over to our slideshow and just work our way through. So more collisions. As I said, we're going to look at 2D examples, we're going to look at explosions, and then we're going to look at collisions at a distance. So first of all, two dimensions. We've already talked about this. I've reminded you in the previous lesson, and we've talked about it when we defined momentum. Momentum is a vector. It needs a direction as well as a magnitude. In one-dimensional problems, that was very easy because we just used plus or minus, and that was our direction. That indicated the direction. It was all we needed to know. In two dimensions, obviously, we need a direction, so we can either decompose it, or we can provide a magnitude and an angle relative to some fixed direction in space. The process, though, is exactly the same. Define your frame of reference. This is no longer one-dimensional. This is now two-dimensional, so you'll need an X and a Y, for example. You could use any combination, as we've talked about when we talked about frames of reference. You could use I's and J's instead of X's and Y's. It doesn't really matter. Once you know the frame of reference, decompose whatever you know about the system into the X and Y. So you might know the initial momentum or the final momentum or part of each or something. Whatever you know, decompose it into your X's and Y's. Add the X and Y components to get the total momentum in the X and Y directions. And the momentum in each dimension will be conserved. So that step 3 is just saying decompose your component momentums. So each object's momentum, decompose it. Add all of the different X components together, all of the different Y components. That's just our mathematical approach to vector addition. Remember, we can just decompose it and add our X's and Y's. So that's just describing mathematical vector addition. You can obviously do that any way you want, but this is going to be the simplest, most reliable method. Decompose and add the components. And that last point, momentum is conserved in each dimension. If total momentum never changes throughout a collision, that's what we've said a collision is, total momentum is never changing, that means that the component in the X direction and the component in the Y direction cannot change during the collision. Because if either of them changed, then total momentum has changed. So we can actually treat conservation of momentum in two dimensions as two separate one-dimensional conservation of momentum problems. And that way, mathematically, it becomes very simple. Generally, I'll stick to subscripts. I've already talked about the idea of doing subscripts and equations as ways to label things. You don't have to stick to that. You can do whatever you want as long as you're very clear and consistent and know what you mean. By all means, if you're doing it in an assignment or a test or exam, and you're using some kind of strange format that you've made up, then do explain it at the start so I can at least follow what you're doing. But you are free to do anything. I will tend to stick with subscripts, but because we've now got multiple objects in multiple dimensions with initial and final velocities and momentum and so on, we end up with things like v sub 1 sub x sub I. Right? So a v with a little 1, a little x, and a little I all next to it. And that can get quite messy. If you're doing it by hand, it can especially get messy. So feel free to come up with other formats. One that is quite common is to use a prime, which is just like a little apostrophe, to mean final. So you forget about using I and F for initial and final. You just use your V or whatever term you're looking at. You just write it without the apostrophe, just as a plain symbol, as I've got here, V1x. That would be your initial. And then V1x prime, so V1x with this little dash, this little apostrophe next to it, that would be your final. So that is one other approach. As I said, whatever you're comfortable with, the goal is to keep track of all the different components. Right? There is a lot to keep track of. We've got multiple objects. At the moment, we're just dealing with 2, but you can certainly use this system, this method, to deal with systems of 3, 4, or however many objects you have. Obviously, the maths gets more complicated, which is why we tend not to do that, but you certainly can. And then you've got, for each of those objects, you've got velocity, momentum, and kinetic energy, and both velocity and momentum are vectors, which means they'll have a direction and a magnitude or two components. So either way, you've got two bits of information to keep track of for each of those. So there's a lot of different variables, a lot of different things to keep track of. So coming up with your method for keeping track of it is very important. Feel free to just copy what I do, but do also feel free to do something else if it is more comfortable to you. So with all of that said, let's crack on with an example. We're going to look at two billiard balls. Both of them have mass 200 grams, which I've chosen just to keep things simple. They collide. The first ball is initially traveling at a speed of 2.9 meters per second directly towards the second ball. That second ball is at rest to start with. After the collision, the second ball travels at a speed of 2.5 meters a second at an angle of 30 degrees below the direction the first ball was traveling in. Right, so notice that odd wording. It's because I have not defined the frame of reference in the question for you. You're free to choose your own frame of reference. So I've worded it slightly oddly, but in order to make it clear, because if I said below the x-axis, that defines x-axis for you. So the question is to determine the speed and direction of the first ball after the collision. If you are comfortable with this sort of problem, with the two-dimensional momentum problem, which I haven't explained to you yet beyond what I just said, do feel free to pause the video and have a go and then see if you get the same answer. But alternatively, obviously, you can just keep watching and I'll work through it. So to start with, we need to define our frame of reference. Since we know that the first ball, which I've drawn here in yellow, is moving directly towards the second ball, we can call that direction one of our dimensions. So I'm going to call that x. By doing that, it means our initial momentum, and therefore our whole momentum, because it never changes, it's the same before and after, that's the point of a collision, our total momentum is only in the x dimension. There is no, or the y component, I should say, is 0. Shouldn't say there isn't one, it's better to say it's 0. So the y component is 0 and we just have an x component. That means that that's a good choice, right? There's nothing wrong with choosing any other frame of reference. You might choose the direction the green ball travels often, or the second ball travels often. You might call that your x, and 90 degrees perpendicular to that would be your y-axis. But I'm going to stick with what I've got here. And you'll also notice I've defined which way is positive. So right, so the direction the yellow ball is initially moving is positive, and the vertical upwards is, well, it wouldn't be vertical if we're looking top down, we haven't specified, but the y moving up on my page is positive. We know the momentum at the start of the collision. We know the initial momentum because we're told the speed of the yellow ball, or the velocity, because we're told the direction as well, and we know that the green ball is at rest. So ball 2, I've added in the 1 and 2 on the balls now since I'm starting to introduce my notation. So P1I, that's the initial momentum of the first ball, is equal to m times V1I, which is 0.58 kilogram meters per second. This is entirely in the x direction. So if we wanted to decompose that, it's very easy because our x component, so P1xi, is 0.58 kilogram meters per second, and our P1yi is 0 kilogram meters per second. For P2i, it is 0. So P2i and P2xi and P2yi are all 0. So the momentum of the second ball initially and its components are all 0 since it is at rest. After the collision, all we know is that the momentum of the speed of ball 2 is 2.5 meters per second at an angle of 30 degrees below our x-axis. I can say below our x-axis now because we've defined that. So below our x-axis. That means that we know the momentum of ball 2. So the total momentum is 0.2 times 0.25, the mass of ball 2 times the speed of ball 2, which is 0.5 kilogram meters per second. That's the magnitude. The direction is still the same, 30 degrees below the x-axis, same direction as the velocity had. We can then decompose that. So that's just our basic trigonometry that we're all used to. We decompose that and we get the x component of our second ball's final momentum as being 0.43301 kilogram meters per second, and the y component being negative 0.25 kilogram meters per second. You'll notice I've put negative 30 into that equation because technically we've defined above the x-axis in the y direction as positive and below it as negative. So you'd stick to the same for angles, positive above, negative below. If you didn't, if you just used cosine of positive 30 and sine of positive 30, you'll still get the right values out, 0.433 and 0.25, but it won't keep track of positive or negative for you. And that's not really a problem as long as you are keeping track of it, which is the point of doing the physics, right? Keep a track of which way is positive and negative, we know by looking at our diagram that we have to have a negative y component and a positive x component for ball 2's momentum. So even if you hadn't put that negative in there and it just told you 0.25 out of the calculator, you should hopefully know to write a negative 0.25 kilogram meters per second. So those are the components for our ball 2's final momentum. We know the initial momentum was just, I'm going to go back a couple slides, was just, well, one slide, was 0.58 kilogram meters per second in the x direction and nothing in the y direction. Ball 2, we've now figured out, has some x component and some y component. So what we need to do is figure out what momentum ball 1 must have in order to keep that total momentum the same. So we need to figure out how much x component ball 1 needs in order to make our x component up to 0.58. And we need to figure out what y component our ball 1 needs in order to make our y component of the total equal to 0, because that's what it was initially. So that's quite easy. We just do those calculations, 0.58 minus 0.433 and 0 minus negative 0.25, which gives us obviously positive 0.25 for that y component. But the x component comes out to 0.14699 kilogram meters per second. So there we've got the x and y components for our ball 1. So that was pretty straightforward. Once we knew the x and y components of ball 2, we just knew to calculate the difference to get the x and y components of ball 1, because we know that the final total momentum has to be the same as it was initially. It's a collision. There's no way for it to change. That means we can figure out the total momentum of ball 1. Sorry, not the total. We've got the total momentum. We can figure out the magnitude of the momentum and the direction. And of course, the question asked for the speed and the direction, which of course is the velocity. Speed is the magnitude of the velocity. So we're asked for the velocity of ball 1. And that means we need to either calculate the components of the velocity and then the magnitude of the velocity, or as I've done here, you can calculate the magnitude of the momentum and then get the magnitude of the velocity from that. So magnitude of the momentum is just using Pythagoras from our two components. So that's just vector addition Pythagoras-ly. It gives us 0.29001 kilogram meters per second. The direction, trigonometry, the inverse tan of the opposite over the adjacent gives us 59.54 degrees or 60 degrees. So 60 degrees above horizontal, and ball 2 was 30 degrees below. What you might notice is that ball 1 and 2 actually happen to be at right angles to each other as they depart this collision. So we can now get the velocity magnitude, as I said, from the momentum magnitude. Just divide momentum by mass, and that gives us a speed, a velocity magnitude of 1.45005 meters per second. The direction is still the same as it was for the momentum. As I said, velocity and momentum always have the same direction. They are both vectors. Momentum is just a different magnitude vector in the same direction as velocity. So that is the magnitude and direction of our velocity vector, but we should present our results. All the information given to us was 2SF. The only one that we weren't sure of was actually the mass. It said 200 grams. That could be 1, 2, or 3SF, but the speeds were given as 2SF, and the angle 30 degrees again could be 1 or 2 SF. So I've stuck with 2SF here, which means I have ball 1 as having a speed of 1.5 meters per second and a direction of 60 degrees above its original direction after the collision. So its original direction is what I've referred to again, rather than referencing my x-axis. I could easily have said 60 degrees above the x-axis as well. So that's the process. I've obviously written more down and talked a bit more than you would normally if you were solving the problem. You would be able to do a lot of that in your head rather than having to do it on paper. But there's nothing fundamentally new there. We've met momentum, we've met collisions, we've met conservation, we've met vectors, we've met vector decomposition, and all of that. We've met everything. So there's nothing new there really. It's just using all those tools that we already have and applying them to a problem like this. Another thing you can do, even though it wasn't asked, if you were interested, is check the elasticity of our collision. Remember that if it's an elastic collision, we have kinetic energy conserved. So kinetic energy initial here was 0.841. It's just the energy of ball 1 because ball 2 was at rest. So 0.84 joules, and kinetic energy in the end, we have to get the kinetic energy of both balls and add them together, and that comes out to 0.8352, which is 0.84. Now, you might look at 0.841 and 0.8352 and think that they're different. Our system has lost energy, but remember that everything was only given to us as 2SF. So to 2SF, our energy hasn't changed. So we can't say that it's lost energy. We would just say that it's elastic because the energy, as far as our precision allows us to know, has not changed. Another example, even though we've done one in full, and you can probably go off and do pretty much any collision analysis now in 2 dimensions, I will do another one for you, which is an inelastic collision. 2 cars sticking together as they crash. Maybe they've got big magnets in their bumpers or something, obviously not perfectly realistic, but we're going to treat it as a collision, and we're going to treat them as perfectly inelastic, and they stick together. So as shown, those 2 vehicles are traveling towards an intersection. They are traveling at right angles to each other perpendicularly, and they crash. We're going to assume the result is perfectly inelastic, and we want to determine the final direction and speed of the cars. The tan car has a mass of 1,000 kilograms, and the blue station wagon has a mass of 1,500 kilograms. So those are our initial values. We've got the velocities in the image, 25.0 I meters per second and 20.0 J meters per second. That's just someone using I and J as their representation of X and Y, right? And there's no real problem with that. You'll see they've also used X and Y in the same image, right? They were just keeping things different. Technically, they're what are called unit vectors, which I haven't introduced. But it basically means if you see I, it's in the X direction, and if you see J, it's in the Y direction. There's nothing more to it than that. So what we're going to do is use the frame of reference that has already been provided. Sometimes questions will provide them, and if they do, you may as well stick with them. If you really wanted to, you could change your frame of reference, come up with your own one and explain why, but usually it's simpler just to stick with the one that's given, because we wouldn't usually provide one that's a bad choice. So the initial momentum has both an X and a Y component, because car 1 has an X component and car 2 has a Y component. So we can just calculate those 2 components, add them together, and that's our total momentum. So car 1 has momentum of 25,000 kilogram meters per second in the X direction, car 2, 30,000 kilogram meters per second in the Y direction. We've defined positive for both of them as the directions those cars are initially traveling. So those are both positive momenta. The total momentum then is just the addition of both of those, 25,000x plus 30,000y. That is our final momentum, our total momentum, our initial total momentum. Therefore, the magnitude, Pythagoras tells us it's 39,051 kilogram meters per second, and trigonometry tells us it's at an angle of 50.194 degrees to the horizontal x-axis. Right, I haven't written that in there, I've just left that as implicit. If you don't specify what the angle is in relation to, the default is normally the horizontal x-axis. So you can leave it if that's how you've calculated it, but if you calculate it in any other way, which is perfectly fine, if you calculate it down from the y-axis, for example, you would need to state that because the default is the horizontal x. Final momentum, we know, will be exactly the same because we are assuming a collision, a physics collision. That's what we're assuming, so no change in momentum. Since the cars are now traveling as a single object, they must be traveling in that direction of the final momentum. Right? That total momentum is not going to change direction throughout the crash. And if our objects are now one object and have a single velocity vector, that velocity vector must be pointing in the same direction as the total momentum vector, because otherwise the total momentum just wouldn't match and it would have changed, and that would be contrary to our assumption. Since the combined mass is 2,500 kilograms, the final momentum must be the same as the initial, so 39,051 kilogram meters per second. Therefore, the final velocity magnitude must be v prime. You can see I'm using that prime notation. V prime is equal to the final momentum over the final mass, and that is 15.6 meters per second. You'll notice I haven't put any subscripts on that v prime because v1 and v2, car 1 and car 2, have merged. They now have the same velocity v, and because it's the final one, I've used the prime, so it just becomes v prime. Since this was a perfectly inelastic collision, we know the kinetic energy will definitely not be conserved. We've got that information already because we're told it's inelastic, and that's what inelastic means, but it's a good exercise to calculate it. So I would recommend taking a moment and just going back, calculating the kinetic energy beforehand and the kinetic energy afterwards, and just verifying for yourself that it does indeed decrease, that we lose kinetic energy. So that's the answer to the question. We wanted the final direction and speed, and the direction was just the same as that of the momentum, 50.2 degrees above horizontal, and the speed was that 15.6 meters per second. So that's that whole question done for us. We're now going to talk about explosions relatively briefly. An explosion is we're familiar with the term from everyday life. It's the idea of something just being, just separating at great velocity. And that's essentially all it means in physics as well, except we don't have to have great velocity, just have things separating. So an explosion is a collision in physics, provided again that we have no net external force or net external impulse, so no force or a really short duration of the explosion. Remember our perfectly inelastic collisions, the idea of two things that are traveling and then they collide and they stick together. An explosion is just that in reverse, two or more things that are stuck together and then they just separate and travel off in opposite directions. That total momentum of the system must be conserved from when they were one object to when it's separated into multiple. There's no net external forces or impulses, then there can't be any overall change in momentum for our system. So that total momentum is still going to be conserved. It's just that one thing has now become two or more things all traveling in different or potentially different directions. So that's all an explosion is. It's the same idea as an inelastic collision, but oppositely. The energy is obviously not going to be conserved because you could start with something stationary and explode it, and now things are traveling all away. So there's gone from no energy to some sort of energy, and that is the conversion of some kind of potential energy within the system into kinetic energy of the parts of the system. So momentum is conserved. We're defining it as a collision, no net external impulse. We must have momentum conservation. Right? That's our blanket rule. If there's no net external impulse, then there must be momentum conservation. The momentum of each part is obviously going to change because they were traveling together and now they're separated. That means the momentum of each part must have changed, but the net momentum, the total momentum of the system, must not change. That's why we can treat it as a collision. Kinetic energy, as I've said, increases, and that is usually going to come from some kind of potential energy. So, for example, a spring might be released. There might be a spring that's been squashed inside the system. It releases and pushes parts apart. That's what we'll look at soon for an example. You may also have a chemical reaction occurring. So things like explosive fireworks, bombs, whatever is exploding, if it's some kind of chemical combustive process, that is a chemical reaction. So that is chemical potential energy being converted into kinetic energy. And finally, you might have biological processes. So when you've got two people that push apart from each other, that is an explosion, but it's converting biological energy that you've stored in your cells and muscles and so on, pushing it apart, turning into kinetic energy. So there are obviously other forms of potential energy that could be used to create the kinetic energy, but these are some of the more common examples. The analysis is exactly the same as what we've been talking about. We just looked at a two-dimensional inelastic collision, two vehicles that were traveling and then stuck together and both traveled with one same velocity and therefore total final momentum. This is exactly the same, but the other way around. Two or more objects that are all traveling with the same velocity initially, and then suddenly all have different velocities after the collision. And so it's exactly the same process, right? But you're just keeping track of all those different terms. So in this case, before the explosion, before the collision, you're going to have every object having the same velocity. And then after the collision, they'll have different velocities, but that total momentum before and after has to be the same. So we're going to look through an example now, nothing too complicated, just the idea of a little hollow cylinder with a ball in it and a spring that's been pulled back and locked in place somehow, and it's going to be remotely released. So you've got a little remote control, maybe an app on your phone, and you push it and it releases the spring, and the spring stretches out, it expands, and it pushes the ball out of the little cylinder as it does so. What we're going to do is assume that there is no net external force or net external impulse during this explosion. So they are either on a frictionless surface or the spring expands really quickly so that the friction that is there doesn't really have any time to act. So we're going to treat it as a physics collision and make that assumption. Suppose the ball has a mass of 5 grams and the shooter with the spring, so that's the cylinder plus the spring, has a mass of 250 grams. The ball leaves the shooter with a velocity of 16 meters per second. How much energy was stored in the spring? So that's the question we're trying to solve. How do we approach it? Well, we know that initially the momentum is 0 because it was all at rest. And then the ball leaves with the speed that we've been given. We never actually stated the shooter was at rest. but we've been told that it leaves the shooter with a velocity of 16 meters per second. We can assume, since it wasn't mentioned, that it starts with no velocity at all. So both objects combined have no velocity. Afterwards, that ball has a velocity. This is a one-dimensional problem. One-dimensional because the ball is traveling in one direction, the shooter is going to recoil in the other direction. So we're going to treat the ball, the direction the ball goes in as positive, and the direction the shooter recoils in as negative. And our initial momentum, as we just said, is going to be 0 because we've said the system is at rest initially. So we've got initial momentum 0, initial kinetic energy 0. Afterwards, we know it's going to have some kind of positive momentum on the ball and negative on the shooter, but they still have to equal 0 because the total system momentum cannot change. So the velocity of the cylinder can be calculated based on that statement, the fact that the total momentum doesn't change, because we know the speed of the ball is 16 meters per second. Therefore, the momentum of the ball, final, after the collision, is 0.08 kilogram meters per second. That's in the positive direction. So therefore, the cylinder must have momentum negative 0.08 kilogram meters per second, because the total momentum still has to be 0. It hasn't changed. There's no net external impulse. We cannot change the momentum of that system. So the momentum of the cylinder, of the shooter component, must be equal and opposite to the momentum of the ball component. But the mass of the shooter is bigger, so its velocity is going to be different to that of the ball. We can just calculate that from the momentum of the shooter. It becomes negative 0.32 meters per second. So the ball is traveling 16 meters per second to the right. The shooter cylinder thing is traveling 0.32 meters per second to the left. So it's negative, it moves to the left. We now know the mass and final velocity of both components, so we can figure out the final kinetic energy. That is just half mv squared for each component. So you can see, firstly, I've done the ball final, and it's 0.64 joules. Shooter final is 0.0128 joules. That gives us a total final kinetic energy of 0.6528 joules. Since the system started with no kinetic energy and it ended with 0.65 joules of kinetic energy, that must be how much elastic potential energy was released by the spring and converted into that kinetic energy. And that was what the question asked. The question asked how much energy was released by the spring. All of it. That's where the energy came from. There was none initially, and then we had some afterwards, and that came from that elastic potential energy. So just like we dealt with energy conservation when we talked about gravitational being converted into kinetic, people jumping off diving boards, we talked about a ball compressing a spring and this gravitational potential and kinetic, and then turning into elastic potential. We can still do things like that with collisions as well, where we sit here and we go, where is the energy to start with? It's still in our system, but it's in our system as elastic potential energy. Then it gets released as kinetic energy when the spring expands and pushes the ball out. Note that the spring may actually have had more than that stored up if there was friction internal to the system. So the ball rubbing on the cylinder or on the spring, or the spring rubbing on the cylinder. If there was internal friction, then that might have released some or lost some of that energy as it was releasing. We know there was no net external impulse, so there was no external friction, but there could still be internal friction. But we're not really going to get into that. I just wanted to point that out in case you did happen to think of that as well. If you had more information, there's a lot more we could calculate as well. If we knew the spring constant, we could figure out how far the spring must have been compressed, because we know that the elastic potential energy is equal to a half kx squared, or vice versa. If you knew the unstretched length and the length it was squished to, then you could figure out the spring constant. So we could figure out more information if we had a little bit more info as well. So there's a lot of analysis we could do on scenarios like this. And the last part of the course is the first half of the course. Last part of the first half of the course is collisions at a distance. And this is not really something we're ever going to come back to or deal with in any more detail than these couple of slides that I'm about to show you. So remember that we talked about forces at a distance. Forces at a distance, we've met gravity, but there are more. We're going to meet electrical forces and things as well. The idea that two objects can have an effect on each other even though they're not touching. So a lot of the collision stuff we've talked about so far has been in contact. We had balls bouncing off each other, cars crashing into each other, springs pushing against balls. We've got things that are touching each other and thereby imparting forces on each other. But we have also got forces at a distance such as gravity. And therefore we can have collisions at a distance. So imagine an asteroid traveling in a straight line, but then it goes near a star. that star exerts a force on the asteroid and it pulls the asteroid towards it. So that asteroid is changing direction. It's being deflected. It is that is a collision. Right? That is a collision. The thing is, if we include the star in our system and we deal with both the star and the asteroid as our total system, then we can treat it as a collision and we can do momentum analysis on that collision. So the total momentum would be conserved. Right? Gravity is a potential energy. It can't change the momentum of the total system because it's internal to the system. Both the masses are in our system now. So if we've got no net external impulse, because there's nothing else acting on these two objects, then we can't have a change in total system momentum. Of course, the star is going to be really big compared to the asteroid. The change in the star's velocity is probably going to be negligible. If you recall, you did in one of the lessons, there was a question about a ball bouncing off the Earth and figuring out the change in velocity of the Earth as a result of the bounce, and it ended up being ridiculously tiny, and it would take a ludicrous amount of time for the Earth to even move the width of one atom. But the ball did technically change the Earth's velocity, just so small, ludicrously small amount. The same thing would probably be true here. An asteroid would change the star's velocity, but very, very minimally. The main problem with with these sorts of collisions is that these forces don't have an outer limit. There's no point at which the collision technically stops. And so it depends on how precise you want to be, because however far away that asteroid is, it is still technically going to be having an effect on it from the star. The closer you get, the bigger that impact, and so you can see that as that asteroid travels closer, so I've drawn the blue dotted line as the original path of the asteroid, and as it gets closer to the star, it starts to pull in, so it curves a little bit. As it gets closer and closer, though, the curve becomes greater and greater until it moves past, and then it becomes less and less until it straightens back out again. So as it gets closer, the strength of that force, and thus the effect on its path, the change in its momentum, gets greater and greater as it travels through. So we don't have this nice uniform process that we see with these collisions from objects being in contact. And there's no actual start and stop to our collision. We could choose a start and a stop point where we would say, right, beyond this point, the effect from the star is negligible, after it is negligible. So we could get around that by limiting our precision and saying, right, for our purposes of our precision, we're only going to care about the asteroid once it's within, 1 light year of the star, and we'll forget about it once it's before that, and after that, we'll say the gravity is too small. So you could figure out processes like that, but even if you do that, the collisions end up looking like these sorts of curves, right? We've got this curved pathway and it becomes mathematically very complex to analyze. So we're not going to do any of this sort of analysis in this course, but I just wanted you to be aware of it. This is a very common sort of process in physics, believe it or not. We don't, not just with stars, but as I said, we will meet electrical repulsion. So the idea of charged particles and also magnets, and they can cause paths like this, deflections like this. The other thing I just want to mention is this diagram. I've shown no change to the star's position. Remember that the momentum of the system must be conserved. So if that green asteroid initially has momentum to the right and now has momentum down, then the star must have a change in momentum equal and opposite to the green one's change in momentum. So the green one's change in momentum is effectively an arrow that points from the right downwards. Right? So it points left and down. So that means the star must have a change in momentum that points right and up. But because its mass is so much bigger, the velocity that that change in momentum equals to is going to be so tiny as to not even be visible if I draw it on this diagram. But there would be one there, just be minuscule. And finally, just to finish off this lesson, is a couple of bits of terminology. We've already met the terms collisions and we defined explosions during this lesson. You may also see the word interactions just meaning collision in general, but really two objects interacting is a very generic term, so I don't tend to use it myself, but you may see it as just a very generic term. The reason it would be used is if they're asking you whether a certain interaction is a collision, things like that. If they're not certain it's a collision, because remember, collision means no net external impulse. If you're not 100% certain, or that's the point of the question is to figure out if it is a collision, then you may just call it an interaction until you're certain. Another common term is scattering, but it's only used for 2 or 3 dimensional problems, because what it means is the direction's changing. the objects scatter, right? To scatter things is just to spread them out in different directions. So when you've got 2 or 3 dimensional problems, then you can cause scattering via a collision. So that's just a bit of terminology, some words that you may see pop up, but generally if you see any of them, just treat it as a physics collision and do the analysis accordingly. So as usual, there's a bit of a review there, but that is, as I said, the end of the first half of the course. So this first half, these first 18 lessons have been purely mechanics. We've talked about the tools we need, so frames of reference and vectors and all of that. And then we talked about simple motion analysis, so just the motion of objects, velocity, distance, displacement, all of that stuff, acceleration, kinematic equations. Then we moved on to Newton's laws and we talked about forces that cause that motion. So the forces that are applied to accelerate objects. From there, we moved on to energy and momentum, and finally, we just finished with collisions. So we've covered a whole bunch of different tools, different laws, different equations, but you'll get a lot of scenarios where different parts of that might all be applicable. And as we move on to the second half of this course, where we start to jump around a little bit between different topics, you'll find that we reference a lot of those ideas again. So we'll start talking about charged particles and how positives and negatives attract each other. But then if we know their masses and we can calculate the force, we can use Newton's second law again and we can calculate that acceleration, and that brings kinematics back into it. And so we keep using all of this stuff. And so that's why we start with this whole half of the course on mechanics, hopefully a fairly in-depth, thorough discussion of mechanics, and that will continue to apply throughout the rest of the course.